Let us talk about Newton-Raphson method. Newton-Raphson method of finding roots of a I think it is visible. Newton-Raphson method of finding roots of a polynomial or transcendental equation. We know the definition of transcendental equation as well as polynomial equation. This is a polynomial equation. Cubic equation actually. While this is a transcendental equation. Or this is a transcendental equation. An equation which involves e to the power x, cos x, log x, this type of functions which are actually itself they are infinite series. So they are termed as transcendental equation. Transcendental equation. Newton-Raphson method is a method which may be employed to find the roots of nonlinear as well as transcendental equation. Okay? And it uses the concept of Rolle's theorem of differential calculus as well as the expansion, Taylor series expansion of a function. How? Let us assume that fx equal to 0 is the equation for which we look for the roots. Clear? Now first we assume alpha naught to be a root of this equation. Alpha naught is this is termed as initial approximation. Okay? Initial approximation of the root of fx equal to 0. So you should remember that f of alpha naught is not exactly 0, is not never exactly equal to 0. This is an initial approximation. Now how do you get this initial approximation? That is why Rolle's theorem of differential calculus or Rolle's theorem of algebra, whatever you say, is employed. In that case, we argue that if this is x and this is fx, and if we have a and b on x-axis to be 2 points where fa and fb are of opposite sign and they are of opposite sign and very close to 0. So this open interval contains at least one. Now by inspection we find this value of alpha naught, which gives an initial approximation of the root of the reference. So if alpha 0 is not equal to 0, this we all should bear in mind. This is the first approximation or initial approximation of the root of this equation fx equal to 0. And then what happens? We correct this alpha 0 by adding a correction value h, and we argue that this h is small compared with alpha naught. This is a small correction, and then we apply Taylor's series approximation. What is the Taylor series expansion of f of alpha 0 plus h? We know that it is f alpha 0 plus h f prime alpha 0 plus h square by factorial 2 f double prime alpha 0 and so on with the last term as h to the power n by factorial n fn alpha 0 plus theta h, where theta lies between 0 and 1. But you don't need this full expansion of the Taylor series, since h is a small correction. H is a very small correction in comparison with the value of alpha 0. So we just ignore the values of h square, h cube and all the higher powers of h. Only this value is comparable with f alpha 0 or alpha 0, whatever you say. So this is f alpha 1, isn't it so? And alpha 1 is the corrected version of the initial approximation. So we assume that this is 0, which gives the value of h as minus of f alpha 0 by f prime alpha 0. Okay? So this is clear. So what will be the value of alpha 1? Alpha 1 will have value alpha 0 minus alpha 1 will have value alpha 0 minus f of alpha 0 by f prime alpha 0, isn't it so? And this is also an iterative process. Or repetitive process. So we repeat this. So what is the recurrence relation? We may easily write the recursive relation or recurrence relation as alpha r equal to alpha r minus 1 minus f of alpha r minus 1 by f prime alpha r minus 1. Isn't it so? Since alpha 1 was alpha 0 minus f of alpha 0 by f prime alpha 0. So from this we write this in the rth step. And this is an iterative process. We move on finding new alphas. So when should we stop? Simply depending on the tolerance level. That is, our target is to find the root of this equation up to a tolerance level. Root of this equation up to, say, 3 decimal places after 0. So we would like to calculate f alpha r and test whether this is less than this. If this is the case, we claim that alpha r is the root of the equation. And this process converges subject to a condition. The convergence condition can be obtained quite easily. But that is a different aspect. I would like to show it in another video.